I really don't get it. Even though I watch videos and tutorials on how to solve Sue ANOVA, I don't understand how to do them at all. I know. Maybe I should just search online about its definition and when to use it.
For today's Stats vlog, we are here to guide you on how to use two-way ANOVA. We hope that you'll be with us through the end.
I'm going to tell you the definition of a two-way ANOVA and when to use it. A two-way ANOVA is an extension of one-way ANOVA that examines the influence of different categorical independent variables on one dependent variable. It is a statistical test that analyzes the difference between means of more than two groups. When should we use two-way ANOVA? We can use two-way ANOVA when you have collected data on a quantitative variable at multiple levels of two categorical independent variables. It is used when there is more than one independent variable and multiple observations for each independent variable.
In the hypothesis test of two-way ANOVA, there are three sets. The first set is the main effect of first factor. This is like the one-way ANOVA for the row factor. Second is the main effect of the second factor. This is like the one-way ANOVA for the column factor. And lastly is the interaction between the two factors. Let us now proceed to the components of the table. The first component of the table is the M or mean. Mean in each cell is the marginal means. Next is the T, where is the total of the cell. You may add all the given number in each cell, whether it's in column or in a row. Next is the N. N is simply the population or the sample size. It can be determined in the number of your respondents. Next is the SS or sum of squares. The SS or the sum of squares per cell is wherein you have to use the formula of SS total in each cell. Next is the G, which is the total of all T per cell. We must always remember that each cell is the sum of each factor. Lastly is the summation of x squared. This is simply the sum of all x squared.
Stage 1 of the two-factor analysis. Total variability. A measure of the amount of variability is simply the variability of all of the data. We combined all of the data in the experiment together and calculate its variability. To get the total sum of squares, we will be using this formula. Summation of x squared minus the squared of the geometric distribution divided by n, or the population size.
Using the given table shown earlier, we can now compute for the SS total. Simply substitute the formula with the given. The summation of x squared is 331,379. G is 3,055, while n is 30. First, square the G value, divide the G squared value over 30, and then subtract the summation of x squared. Our SS total would be equal to 20,278.167. For our DF total or degrees of freedom total, simply subtract n minus 1. Our DF total would then be 29.
Moving on to stage 1 of the two-factor analysis between treatments variability. The between treatments variability is measured by the variance of the means. To find the sum of squares between, we have to get the summation of t squared divided by the sample size minus the squared of the geometric distribution divided by the population size.
Again, substitute the formula with the given. Do not confuse the capital N with small n, as these have two different values. After substituting, proceed to do the following operations. As for the DF between, all we have to do is subtract the number of cells to 1. Since we have 6 cells, 6 minus 1 is equals to 5. That would be our DF between.
Next is the within treatments variability. In addition to the between treatments variability, there is variability within each treatment. The within treatments variability will provide a measure of the variability inside each treatment condition. Now, to find the sum of the square within, we need to get the summation of the sum of squares of each treatment.
With the given sum of squares from the table, all we have to do is add all the values, which will give us 13,684. For DF within, since we have 5 samples per cell, we will subtract 1 to each, and then and add all values. Our DF within is equal to 24.
Stage 2 of the two-factor analysis. Factor A. To find the sum of squares of factor A, we need to look for the summation of t squared row divided by the sample size row minus the square of geometric distribution divided by the population size.
If we go back to the table, we could see that the total t per row is computed. Get the t value of row 1 and row 2, square each of them, and divide it by the total number of samples per row. After that, square the g value and divide it over 30. Subtract the two computed values and you will get 1140.834. To get the DF of factor A, just subtract number of rows minus 1.
Now for factor B, to find the sum of squares of factor B, we need to look for the summation of t squared column divided by the sample size column minus the square of geometric distribution divided by the population size.
This time, instead of rows, compute the t values per column. Since it is already given in the table, square the t values per column, divide it by the total number of samples per column, then subtract the value from the g squared over n value. SSB is equals to 4,926.667. Same as for the rows, simply subtract the number of columns minus 1.
Factor A and B interaction. To find the sum of squares of A and B, we need to get the sum of squares of between treatments minus the sum of squares of factor A minus the sum of squares of factor B.
Since we have already solved for SS between, SSA, and SSB, all we have to do is substitute with the given and do the operations. SS factor A and B interaction would be equal to 526.666. For the DF, it would be the same. Get the computed DF between, DFA, and DFB from earlier and subtract all values. Our DF factor A and B interaction would be 2. Now, we move on to the mean of squares. Mean of squares are estimates of variance across groups that are obtained by dividing the sum of square values to degrees of freedom. To get the MS within, simply divide SS within to DF within. Substitute the formula with the values and equate. Our MS within would be equal to 570.167. For MS between treatments, it is divided into 3, which are primarily factor A, B, and A and B interaction. Likewise, to get MSA, divide SSA to DFA, and that would give you 1140.834. For MSB, divide SSB to DFB, which would be equal to 2463.335. Lastly, for MSAB interaction, divide the SSAB to DFAB, which is equal to 263.333. After getting the mean of squares, all we have to do now is find the F ratios in order to decide for the hypothesis tests. All are done by dividing the MS factor value by MS within value. For FA, divide the mean square of factor A by the MS within value. That would be 2.001. MSB divided by MS within is 4.320. And last, MSAB over MS within gives us the F ratio of 0.462. One last important step is to determine the strength of association between effect and the variable by getting the eta squared value. To get the value, simply divide SS between by SS total, which is equal to 0.325. After all those computations, here is the summary table of two-way ANOVA. For the top row, we have our source of variation, the sum of squares, degrees of freedom, mean squares, F ratios, and the effect size. Under source of variation, we have between treatments, factor A, in our case is gender, factor B, which is consumed sugar, A and B interaction within treatments, and the total. To get the F-crit value, we used the Excel software, but you may refer to other softwares such as SPSS or search online for F-crit values. For the row or factor A, the F-crit value is greater than the F obtained, which means that the null hypothesis is true. there is no significant difference between rows. For the column or factor B, the f obtained is greater than the f crit and thus the null hypothesis is rejected and the alternative hypothesis is accepted. There is a significant difference between the columns. Similarly, our f obtained for A and B interaction is greater than the critical value. The null hypothesis is rejected and the alternative hypothesis is accepted. Therefore, there is a significant interaction between the factors. And that is all. Thank you for watching. We hope that you learned something new today. Until next time.